Okay, so looking at calculations here of relating wavelength or frequency to energy of light. And we just talked about on the last page, we've got a couple examples here of where this might apply. So the first one, we've got some green light. The wavelength of the light is 500 nanometers. What energy in joules, what is the energy in joules of one photon of the green light? So we're going to relate energy to wavelength. Right? We did just talk about that equation. We would need Planck's constant and the speed of light, and we need to divide those by the wavelength. Now, just like we saw in the previous examples, where we were just relating frequency and wavelength, and the units on our wavelength should be meters here to cancel with the units that are coming from the constant. So let's change from 500 nanometers to meters. So 1 meter again is a billion, or 10 to the 9th nanometers. And that would be 5.00 times 10 to the minus 7th meters. Okay. Now, from there, this is really just plugging into the correct equation. So if you can kind of keep track of your equations, or even just keep track of your units, a lot of these calculations are just going to involve getting the units in the right place. H here, or Planck's constant, is 6.626 times 10 to the minus 34th, and that is joule seconds, so joules times seconds. The speed of light is 3 times 10 to the 8th meters per second. Okay, and that'll cancel out the seconds there. Divide that by our wavelength, 5 times 10 to the minus 7th meters, right? That'll cancel out meters, and this will just leave us with joules. So this would be the energy of one photon of this light with a 500 nanometer wavelength. So 6.626 times 10 to the minus 34th times 3 times 10 to the 8th divided by 5 times 10 to the minus 7th. And right, this should be a pretty small number because a photon is not very big, so the individual energy of a photon is not going to be a lot. Now we're at 3 significant figures. The only data we had here was our wavelength we started with. So 3.98 times 10 to the minus 19th joules. Right? So keep that in mind. If you're calculating the energy of a photon, that should be a pretty small number, right? Even if it's fairly intense light, if it's just one photon. Okay, now another example here, right, that will extend this a little bit more. In fact, it may be into territory we recognize from some previous chapters. Energy of 2 times 10 to the second, right? So 2 times 10 to the second would be 200 kilojoules per mole. Is required to cause a cesium atom on a metal surface to lose an electron, right? Kilojoules per mole, that's more like an enthalpy, right? This is the energy associated with a chemical process, right? And we have the units to match, kilojoules per mole. What is the wavelength of light that would be needed? Okay, so this is related to the problem up here in that we're trying to relate wavelength to energy. Now, in this case, we're going to end up solving for wavelength. So if I just rearrange the equation that I had up here, wavelength would equal hc over E, right? So just dividing both sides by E and multiplying both sides by wavelength, we could rearrange that equation. Now here, what I need here is the energy of each individual photon. This is not the energy of a photon. This is the enthalpy value for this entire process. So what I need to do is take this value and change it to how much energy there is per photon, and I want that in joules. So this is maybe the tricky part of this question, is recognizing this difference. If you start with kilojoules per mole, what you want to do is change to joules per photon. Right? You need 2 steps here. Kilojoules to joules shouldn't be that challenging, because that's just the prefix kilo. There's 1,000 joules per every kilojoule. So multiply by 1,000, that'll get us to joules per mole. Right? The maybe trickier step here is I need a mole on top here to cancel out moles on the bottom. So 1 mole of photons is 6.022 times 10 to the 23rd photons. That is how we will introduce the required relationship to each individual photon into this equation. That would cancel out moles, right? Now I have joules per photon in terms of this energy. So if I multiply this out, 2 times 10 to the second power, which is 200 times 1,000, and then divided by Avogadro's number, I get 3.321. I'm going to keep I really only have 2 sig figs here. I'm going to keep a couple extras in terms of what I write down. And I can't keep it in the memory because I'm using the little solar calculator. Right? That's how many joules there are per photon. Now, look back up here. We never say per photon here. We really just understand this equation relates to a photon. So don't get caught up thinking I'm going to have to cancel out photon here. We're just going to drop that photon and plug this energy in joules here, and then all the units work out just fine. But keep in mind, those 2 equations are just describing photons. You can't use that with other types of energy that you might plug into that equation. But now I can plug this in here, the wavelength of this light. Planck's constant, 6.626 times 10 to the minus 34th joule seconds. Speed of light, 3 times 10 to the 8th meters per second. And now I'm dividing by joules, 3.321 times 10 to the minus 19th joules. So in this case, joules is canceling, seconds is canceling. This is going to give me this wavelength in meters. Right? But I've got a lot of scientific notation I've got to plug in correctly and properly here to make sure this works out. So 6.626 times 10 to the minus 34th. Multiply that by 3 times 10 to the 8th. And then divide by 3.321 times 10 to the minus 19th. And that gives me 5, and just 2 significant figures here, so actually it wouldn't be 5, it's 5.985 here in the coefficient in the scientific notation, so that's going to round to 6.0 to only 2 significant figures, times 10 to the minus 7th meters here. Now 10 to the minus 7th meters, that might be better reported in nanometers. So if I multiply that by 1 times 10 to the 9th, that would convert it to nanometers, right? And that would be, so it's 598.5 nanometers. It's really kind of hard to report that as 2 significant figures, right? Because we'd want to round it to 600 nanometers, but since it's 2 significant figures, that should be 6.0 times 10 to the 2, 10 to the second nanometers if we do convert it to nanometers. Now that wasn't mentioned in the problem, just says what wavelength, but that is light that would fall into the visible range, which is normally reported in nanometers. Okay, there's good for those 2 problems. Let's continue on to the next page. I see the way the notes break down. We really just have a picture on the next page. This picture is not great in a black and white printed copy of the notes. So maybe let me start to explain what we're trying to show here. The way light interacts with atoms is by moving electrons around inside the atoms. And what we see for each individual element is what is called an atomic spectra. In the atomic spectra, we see lines, right? And these represent, you can see the direction of wavelength changes here. These lines represent different colors of visible light. So what we see here in the atomic spectra is that each different element, so sodium, mercury, lithium, and hydrogen are shown, has a different internal electronic structure. All of the lines we see here correspond to electrons moving between energy levels within the structure of an atom. So we really just take kind of a cartoony picture of so I'm trying to write NUC there for nucleus, right? If that's the nucleus of an atom, we can kind of think of sort of places around that atom where the electrons can live. And this is one of the discoveries of early 1900s, that electron position is quantized, that electrons can only have particular energies. So imagine, atomic spectra, we put some energy in. It could be from burning a sample. It could be from running an electric current through it. But maybe there's an electron that normally lives here in the lowest energy level. We run a current through and the electron moves up here to this higher energy level. Now, once that excitation, that electric current goes away, the electron has some possible things that could happen to it. It could fall back to these different energy levels that are closer to that positive charge of the nucleus. There's an energy difference between the electron being here, far away from the nucleus, being closer to the nucleus, even closer to the nucleus. So each of these changes in energy as the electron falls back down energy levels corresponds to a type of light. So for each of these, so h nu here is often a way you indicate light, because that's Planck's constant times frequency, which is equivalent to the energy of the light. Each of these transitions from the electron falling down would have a different energy. So by evaluating the information in these spectra, we can actually learn about the internal structure of atoms. And that's what we're going to focus in on more next time. It's nice to see the colors in these pictures, so you may want to look this up in your textbook for sure as well.